The pillars of computer science, unveiling its core disciplines and innovations in an era dominated by digital transformation. Computer science stands as the backbone of technological advancement. From algorithms that power artificial intelligence to systems managing global data networks, its influence is omnipresent. This in-depth exploration delves into the foundational research areas within computer science, revealing how these disciplines drive innovation across industries and shape our modern world. Algorithm design and analysis. At the heart of computing lies the study of algorithms, precise instructions that solve problems efficiently. Researchers continuously develop new methodologies to optimize performance metrics such as time complexity and space usage. Different algorithm classes address distinct computational challenges. For instance, divide and conquer techniques excel at solving complex problems through recursive subdivision. Greedy algorithms make optimal local choices at each step, often leading to globally efficient solutions when applied correctly. Dynamic programming stores intermediate results to avoid redundant calculations, ideal for optimization problems with overlapping subproblems. Performance evaluation involves rigorous analysis using Big O notation to quantify scalability characteristics. This enables developers to predict behavior under various input conditions. Emerging fields like quantum computing are pushing algorithm design boundaries, requiring entirely new approaches to computation and problem-solving paradigms. Data structures fundamentals. Selecting appropriate data structures forms the foundation of effective software development. These structures organize information in ways that facilitate rapid access and modification operations. Fundamental categories include arrays, linked lists, trees, and graphs, each with unique advantages for different use cases. Hash tables provide near-instantaneous lookups, while binary search trees maintain sorted orderings. Advanced implementations incorporate self-balancing mechanisms. Red-black trees and AVL trees ensure logarithmic time complexities for insertion/deletion operations despite dynamic changes. Certain applications require specialized structures. Bloom filters minimize memory overhead for probabilistic membership testing, making them invaluable in distributed systems. Artificial intelligence and machine learning. Modern computer science thrives on AI advancements that enable machines to learn from experience and make intelligent decisions. Supervised learning methods form the bedrock of many practical applications today. Deep learning architectures have revolutionized pattern recognition tasks. Convolutional neural networks achieve state-of-the-art performance in image classification challenges, outperforming traditional feature engineering approaches. Natural language processing benefits immensely from transformer-based models. BERT and GPT variants demonstrate remarkable capabilities in understanding context-aware textual patterns. Ethical considerations now play critical roles in AI development. Bias mitigation strategies and explainability frameworks help ensure responsible deployment of machine learning systems. Software engineering principles. Creating reliable software requires adherence to established engineering principles. Modular design patterns promote code reusability and simplify maintenance processes over time. Design patterns serve as reusable blueprints for common architectural challenges. The model view controller paradigm separates concerns effectively, enhancing system extensibility. Agile development methodologies prioritize iterative progress over rigid specifications. Continuous integration practices ensure early detection of potential issues through frequent automated testing. Security remains paramount in contemporary software development. Secure coding standards combined with threat modeling help identify vulnerabilities during implementation phases. Operating systems development. Operating systems manage hardware resources while providing essential services to application programs. Their kernel components handle fundamental functions like process scheduling and memory management. Multitasking capabilities rely on sophisticated scheduling algorithms. Round-robin and priority-based approaches balance CPU utilization against responsiveness requirements differently. Virtualization technologies extend OS functionality by creating isolated environments. Containerization solutions like Docker revolutionize application deployment workflows significantly. Modern operating systems integrate advanced security features. Mandatory access controls prevent unauthorized resource access, protecting both user data and system integrity. Networking and distributed computing interconnected devices require robust networking protocols to communicate reliably. TCP/IP suite forms the standard framework for Internet communications, enabling seamless device interactions worldwide. Distributed computing leverages multiple interconnected computers to perform tasks collaboratively. MapReduce architecture demonstrates effectiveness in handling massive parallel computations. Cloud computing has transformed how businesses deploy infrastructure. Virtual servers offer scalable resources without requiring physical hardware investments upfront. Blockchain technology introduces novel consensus mechanisms. Decentralized networks validate transactions transparently, reducing single points of failure in financial transactions. Human-computer interaction user interface design focuses on creating intuitive experiences between humans and digital systems. Cognitive load theory informs layout decisions that enhance usability significantly. Accessibility guidelines ensure equitable access to technology. Screen readers and voice assistants enable users with disabilities to interact meaningfully with digital platforms. Virtual reality interfaces push interaction boundaries further. Haptic feedback systems provide tactile sensations, increasing immersion levels substantially. Usability testing reveals critical insight into real-world application scenarios. Iterative improvements based on empirical observations create more effective user experiences systematically. Quantum computing foundations. Quantum computing represents a radical departure from classical computation principles. Quantum bits, qubits, leverage superposition states to represent multiple values simultaneously, offering unprecedented computational power. Quantum entanglement enables instantaneous correlation between qubit states, facilitating breakthroughs in cryptography and optimization problems. Shor's algorithm threatens current encryption standards by demonstrating efficient prime factorization abilities. Error correction presents significant challenges due to decoherence effects in quantum systems. Surface codes show promise in mitigating errors through clever redundancy strategies. Current hardware limitations restrict widespread adoption, but substantial investment indicates imminent commercialization possibilities across various scientific domains. Computer security and cryptography. Cybersecurity remains crucial as digital threats evolve constantly. Encryption techniques protect sensitive information through mathematical transformations that obscure original contents. Symmetric key algorithms like AES provide fast encryption/decryption rates suitable for securing communication channels efficiently. Public key cryptosystems enable secure message exchanges without prior shared secrets. Cryptographic hash functions ensure data integrity verification. SHA-256 generates unique representations for any given input, serving as fingerprints for verifying authenticity consistently. Zero-knowledge proofs allow identity validation without exposing private credentials explicitly, enhancing privacy protections dramatically in authentication scenarios. Parallel and concurrent processing. Leveraging multi-core processors optimizes task execution time significantly. Parallel processing divides workloads into concurrent threads that execute independently, accelerating overall completion speeds. Concurrency models like actors and futures manage asynchronous operations gracefully. Actor model organizes behaviors as independent entities communicating via messages rather than direct method calls. Deadlock prevention strategies safeguard against circular wait conditions that can paralyze entire systems unexpectedly. Resource allocation graphs help detect potential deadlock situations preemptively. GPU computing harnesses graphical processing units for general-purpose tasks, achieving superior floating-point operation capacities compared to conventional CPUs alone. Database management systems. Effective data storage solutions rely on well-designed database systems. Relational databases organize information through structured query languages that support complex relationship definitions. NoSQL alternatives provide flexible schemas adaptable to evolving business needs rapidly. Document stores like MongoDB accommodate hierarchical data representations intuitively. ACID properties guarantee transaction reliability across diverse database architectures. Atomicity ensures either complete success or total rollback of database modifications. Distributed database systems overcome geographical constraints by replicating data across multiple nodes strategically. Master-slave configurations balance availability with consistency requirements carefully. Scientific computing applications. High-performance computing enables simulations that drive discoveries in numerous scientific fields. Finite element analysis helps engineers test structural designs virtually before construction begins. Climate modeling predicts environmental changes accurately by simulating atmospheric dynamics precisely over extended periods. Supercomputers run complex meteorological simulations routinely. Bioinformatics combines computational biology with data analytics to understand genomic sequences better. Sequence alignment algorithms reveal evolutionary relationships among species efficiently. Computational physics calculates particle interactions mathematically, allowing scientists to explore phenomena otherwise impossible through experimental means exclusively. Mobile application development. Smartphone ecosystems require specialized development approaches tailored for touchscreen interfaces. Native app development utilizes platform-specific tools for optimal performance outcomes generally. Hybrid frameworks combine web technologies with native APIs for cross-platform compatibility purposes conveniently. React Native offers compelling options for building mobile apps efficiently. Progressive web apps deliver desktop-like experiences through browser capabilities alone. They eliminate installation friction commonly associated with traditional app downloads traditionally. Augmented reality integrates virtual elements into real-world surroundings seamlessly. ARKit and ARCore provide powerful tools for developing immersive mobile applications innovatively. Internet of Things, IoT, connected devices forming smart environments depend heavily on IoT infrastructures. Edge computing reduces latency by processing data closer to source locations rather than central cloud servers exclusively. Standardized communication protocols ensure interoperability among heterogeneous devices naturally. MQTT provides lightweight messaging transports ideal for constrained network environments typically. Data aggregation techniques extract meaningful insights from sensor outputs frequently. Time series databases store sequential measurements appropriately for trend analysis effectively. Privacy concerns necessitate robust security measures inherently built into IoT implementations fundamentally. End-to-end encryption protects transmitted information adequately regardless circumstances prevailing. Cloud computing architectures. Scalable IT infrastructures benefit greatly from cloud computing models available currently. Infrastructure as a service offerings let organizations rent compute resources, instead purchasing equipment outright necessarily. PaaS platforms streamline application deployment by providing pre-configured runtime environments readily accessible. Developers focus primarily on writing code rather than managing underlying infrastructure actively. Serverless computing abstracts away server administration responsibilities completely. Functions execute only when triggered by events happening spontaneously. Multi-cloud strategies distribute workloads across different providers deliberately to avoid vendor lock-ins potentially damaging long-term objectives adversely. Conclusion: from theoretical foundations to cutting-edge innovations, computer science encompasses a vast landscape of knowledge shaping our digital future profoundly. Each discipline contributes uniquely towards advancing technological frontiers relentlessly. Understanding these core research areas equips professionals with necessary insights to navigate complexities inherent in modern software development landscapes successfully. Embracing continuous learning becomes essential in this ever-evolving field dynamically.